Hello again, AP Physics students. In today's lesson, which will be a very short one, we're going to talk about the internal resistance within a battery. I did just want to make one quick point in talking about internal resistance in a battery and also just the internal resistance within the wires that connect our different circuit elements. Unless we're looking at a lab situation and we're looking at just standard assigned questions within either assignments or on the AP exam, we're always going to assume that the wires themselves have negligible internal resistance, and likewise with the batteries. So, whenever we're dealing with circuit analysis, those are a couple of factors that we do not need to consider. But like I said, in more of like a realistic lab setting, this is something that we're going to examine and just briefly talk about right now. So just to kind of go through just the general idea of this, uh, because a battery is a real object made of matter, there is going to be some resistance to the flow of charge within the battery itself. Now, if you look at the actual picture I have for this is a really simple electrical circuit. I just have like a battery connected to like a single resistor. The resistor on the outside, I'm using capital R to represent its resistance, and the current through the battery is just capital I. Now, if you take an actual battery and you look inside of it, one way we can model the internal resistance within the battery is you can just say within the battery, we have another very small resistor. And this resistor in the battery has a resistance that is lowercase r, and that resistance lowercase r is what we refer to as the internal resistance. And that's the model that we're simply going to use. So we'll kind of clarify between these different variables in a moment here. Like we have one variable that's v subscript t, and we also have a variable representing epsilon. And then the whole idea is we're just going to try to identify in actuality what effect does some small internal resistance within a battery have on the circuit itself. We've seen this variable before, but I mean, it may not written like this, but another word to describe voltage, as we talked about back in Physics 30, is referred to as electromotive force. We'll use a variable now to represent it, which is going to be epsilon. We'll come back more to this epsilon variable later when we start talking about magnetic flux in the magnetism unit. In terms of what the electromotive force is, now we'll just call it EMF for short. So the EMF is the maximum possible voltage the battery can provide between its terminals. So there's no way that the battery voltage can be anything that's actually higher than what the EMF is. We also have the terminal voltage. And what the terminal voltage is that is the actual voltage the battery provides after you've accounted for the internal resistance within the battery. So what ends up happening in actuality is the terminal voltage is going to be a little bit less than what its maximum possible value would be. And again, its maximum possible value is going to be the EMF. And specifically, it's going to be less than the EMF by an amount that is going to be capital I, which is the current through the circuit, multiplied by the internal resistance of the battery. And we'll do like a very quick derivation to show that this is the case. So let's say that you look at Kirchhoff's voltage rule as an external view of the battery. When I say external view, it just means that I can't see inside of the blue here, okay? All I see is that I have a resistor on the outside, there's current I through the circuit, and there's the battery voltage, which is the terminal voltage. So if we apply Kirchhoff's voltage rule to that loop, just the outside loop where we can't see inside of the battery, it's a really simple equation. It would just be the terminal voltage, which is positive for the battery, And then you would subtract the voltage across the big resistor, capital R, which would just be equivalent to the current through that resistor times its resistance value. So what that'll do is it'll give me an equation that tells me the terminal voltage is equal to capital I times R. Now, an internal view is we're going to go through the loop, but now I can actually see these elements that are within the blue here. So I can see this battery, which represents the EMF, which is the maximum possible voltage you can have, and also the internal resistance within the battery. So if we apply Kirchhoff's voltage rule, which again is the sum of the voltage around this loop is equal to 0, the equation is a little bit more complicated. So if we were to start at the EMF, so we'd have positive voltage representing the EMF, which again is like the maximum possible voltage you can have. And if we move in a direction that's going to be counterclockwise, then we would go through resistor capital R. So we have a voltage drop across that. That would be equivalent to I times capital R. And then we go through the internal resistance. So we are just modeling it as if we have like a mini resistor within the battery. And that's capital I times little r. And what I'm going to do here is in the equation where I have capital I times R, I'm just going to plug in the equation for the terminal voltage here. So if you do that, you would then have epsilon minus the terminal voltage is equal to I times R. And if you manipulate the equation for your terminal voltage, you then have your terminal voltage is equal to epsilon minus I times little r. And again, that just represents what the terminal voltage is. So the EMF is like what the maximum possible voltage is. Now, obviously, if you don't have any internal resistance, then the EMF is just equal to the terminal voltage. But if you do have internal resistance, then you would take your maximum possible voltage, the EMF, subtract I times R, which is the voltage drop across the internal resistor, and that would be equal to your terminal voltage. Now, there's actually a couple things that I want you to do related to, well, one of them is directly related to this lesson and one of them is not. So the first thing that's not directly related to this lesson is there's just an additional question that you need to complete in the complex circuit analysis section of assignment number 4. Okay, that's question number 3. Now, the other thing that you need to do is I want you to get started on a lab that's referred to as, I think it's called Electrical Circuits Lab. There's actually 2 mini labs within this, and you'll have a couple of days to kind of complete this lab over. So not just within this current class. The first one is just distinguishing between resistors that are ohmic and non-ohmic. And we talked about the difference between ohmic and non-ohmic resistors in a previous lesson. The other one is dealing with specifically the terminal voltage and the internal resistance of a battery. Okay. Now, in that lab, just a bit of a note. At some point in that lab, you're going to have to construct a graph. I believe that on the y-axis is going to be, I think it's 1 divided by your current. And then on the x-axis, I think it's your equivalent resistance or something like that. Now, when you draw a graph, you're going to get a direct variation. Okay. Now, the one thing I just want to point out here is when you get the direct variation, it should be partial. Okay. You're going to have a y-intercept that's very, very close to the origin. So let's draw a graph that maybe just looks something like this. I mean, obviously, I could scale it to maximize the amount of space that line occupies, but you're going to have a small y-intercept. Usually, if we plot a bunch of data and we're just trying to draw a line of best fit through it, we really like the line to go through the origin. But in terms of like doing a proper analysis in this lab, you really do need to have a small y-intercept. So don't make that y-intercept equal to 0 when you're trying to draw a line of best fit that does go through the data. Okay, it should be a very small y-intercept. It should be positive. Okay, small y-intercept that's positive, and that'll allow you to complete the proper analysis for the lab. Okay, so that's it for, like I said, this is probably the shortest lesson you'll ever have in a Physics 2030 or AP Physics course. So again, just complete that question number 3, and then just go ahead and get started on that electrical circuits lab. And I'll talk to you in the next lesson, which will be getting into some more details about capacitors.